Hello students. So in this lecture we are going to understand the principles of spectroscopy. At the very outset, let us take the contents of spectroscopy that we have to understand. So we'll be starting from the introduction, then principles of spectroscopy, definition, origin of spectrum, classification of spectroscopy. In this, we will deal with atomic, molecular, and selection rules. And the last one is table of relation, that is table of relation between electromagnetic spectrums, type of spectroscopy, and the energy changes which are involved. So to start with, what is spectroscopy? Spectroscopy is a technique that deals with the production, measurement, and interpretation of spectra arising from the interaction of electromagnetic radiation with matter. So as we all know, what are electromagnetic radiations? We all have studied at our graduation level, school level. So we do have a basic idea of what is electromagnetic radiation, what are the components, how electromagnetic radiation interacts with the matter present in universe. Now, what is matter? So needless to mention here that matter is something which has its own weight that can participate in this universe in interaction with lot more radiations or other kind of phenomena. So spectroscopy on a whole, we can say that is a branch of science in which electromagnetic radiation of particular wavelength or range of wavelength is used for quantitative and qualitative analysis of matter. Now, there are different spectroscopic methods that are available for solving a wide range of analytical problems. Now, you can imagine what kind of analytical problems we can deal with. So, if you think on a daily life basis, then we are going through a lot of things which already involves spectroscopy techniques. Okay, so we will try to understand this in detail as the lecture moves forward. So now, why spectroscopy? Why are we learning spectroscopy? Because it has wide applications. It has its use in environmental analysis, pharmaceuticals, academic R&D, food and beverages, materials technology, forensic sciences, astronomy, and lot more fields. So now the methods that differ with respect to the species to be analyzed can be categorized into molecular or atomic spectroscopy, or it can be a radiation to matter interaction, or it can also be understood in terms of which region of electromagnetic spectrum is being used for the analysis. So complete electromagnetic radiation, as we all know, is divided into different kind of regions, which has its own frequency and which has its own wavelength. So we can say that particular region of a electromagnetic spectrum corresponds to a definite spectroscopic techniques, and consequently it leads to a particular kind of application. So we will study this in detail in future slides. Now, interaction of radiation and matter. As you can see in the figure, an incident light beam, how it strikes a matter, it can get absorbed, it can get photoluminate, it can transmit itself, it can scatter, or it can reflect back. So if a matter is exposed to electromagnetic radiation, example infrared light or radiation that can be absorbed, transmitted, reflected, scattered, or undergo photoluminescence, it all these kinds of phenomenon which are taking place are nothing but these are the parts of the interaction of incident radiation with matter. Now, here the well-known electromagnetic spectrum I'm trying to show you. So there's nothing new with this, but just to get a quick revision of the things, I have plotted this here. So we can start with radio waves. As you can see, from 1 meter, then microwaves, then it is 10 to the power minus 1 to 10 to the power minus 3, then we have infrared 10 to the power minus 4 to 10 to the power minus 5, then we have visible light which are normally our eyes can see, so zero point 0.4 to zero point 0.7 micrometer, and then we have ultraviolet, okay, we have x-rays, and we have gamma rays. So you can see here that long wavelength corresponds to low frequency, okay, and vice versa, short wavelength corresponds to high frequency. In the next figure, we can see how a visible spectrum can be further expanded into different light, into different colors. So as we all know, we are very much familiar with Vibgyor. So violet, indigo, blue, red, and all these colors are there in our visible spectrum with definite kind of wavelength. So we can use each section of this electromagnetic spectrum to analyze or to detect different kinds of samples which we want to study, different kinds of vibrations in the sample, electronic transitions happening in the sample, and what kind of rotations are going on atomic scale or molecular scale. So a lot more information can be derived from, you know, these different kinds of sections or regions of electromagnetic spectrum. Okay, so now we will deal with properties of waves. This again, these are the revision of the things which we have already studied. So just to revise, wavelength, what is wavelength? It is distance between two nearest crest or trough. So in the form of wave, you can see in the figure that the difference between two crests at the top are or the two troughs are known as a wavelength. Now what is frequency? Number of wave cycle in a given time, and the unit is hertz. What is amplitude? Wave's height or length can be measured in the form of amplitude. Now, what is the relationship between frequency and wavelength? C equals to mu lambda, where C is nothing but a speed of propagation, which is near about 3 into 10 to the power 8 meter per second. Then we can see that what is energy in the terms of frequency of light. So energy of light can be calculated by multiplication of h, which is Planck's constant, by frequency of the light. Now Planck's constant value, the well-known value, is 6.16 10 to the power 34 joules second. Okay, now what are the spectroscopy common terms? Principle means something which is based on the measurement of spectrum. What is a spectrum? A graph or a plot of intensity of absorbed emitted radiation by sample versus frequency or wavelength. Now, what is an instrument known? Instrument is a spectrometer that is designed to measure the spectrum of a particular sample using this particular kind of radiation. Now, what are the types of spectra that we can obtain? There are three kinds of spectra that we can obtain. These are absorption, emission, or they may be continuous. So, if we take in detail the kinds of spectra, you can see from the figure that if a high density hot matter is radiating, then continuous spectrum can be expected. Hot gas is radiating, then emission spectrum can be expected. And if a cold gas is radiating, then absorption spectrum can be accepted. In the figure itself, you can detect, you can see very well, and you can try to understand what are the difference between the nature of these spectra, whether it is continuous, how the emission is taking place, and what kind of absorption spectrums we can obtain. So to study in detail, we can say that continuous spectra is nothing but spectra obtained when white light passes through a prism. Absorption spectra is obtained by absorption of electromagnetic radiation to the atoms, ions, or molecules of sample. Let's say, for example, UV visible or infrared radiations. Then third category is emission spectra, spectra obtained by emission of electromagnetic radiation to the atoms, ions, or the molecules of the sample. The technique's example is the mass spectroscopy. Now, absorption of radiation. At what level and how the absorption of radiation can take place? So just try to understand that there can be different energy levels. Okay, so the lowest most energy state is known as the ground state, where the atom is residing in a resting phase. Now, when it gets excited and reaches another higher energy levels like E1, E2, E3, E4, etc., then it has to absorb some amount of energy to get promoted to higher electronic states. Now, the difference between the higher and the lower energy levels can be denoted in the form of difference of energy, that is delta G. Okay, so we can say that in short, molecules absorbs energy in the region UV or visible promoted to higher energy level E1, E2 or E3. Now, what is vibrational energy levels? Molecules absorb infrared radiation and get promoted from one vibrational level to another vibrational level, or they simply vibrate with higher amplitude. Less energy is required than electronic energy level. So we can say that a molecule requires more energy to radiate to higher energy levels in electronic states, whereas when only vibrational energy level has to be disturbed, relatively lower energy has to be provided. Okay, so the third concept is the rotational energy level. What is it? Energy required is smaller than vibrational energy level, and the phenomenon is same. There are different levels of rotational energy, and but the only difference is you require really less amount of energy to excite a molecule from its lower rotational energy level to higher rotational energy level. Now, atomic and molecular absorption. Atomic absorption for monoatomic particles and polyatomic particles, we will try to understand how it differs. For monoatomic particles, absorption spectra consists of a few well-defined frequencies. Now, these are known as absorption lines. For polyatomic means many atoms together and participate in atomic absorption, then the spectra is more complex. And the number of energy states is huge. Okay, the energy associated with the bands of a molecule is made up of three components: electronic, vibrational, and rotational. Altogether, we'll be looking at the figure in the next few slides, and we will try to understand in a better way. The third category is molecular spectrum. Molecular spectrum can be easily understood in the form of a band spectrum. Band spectrum is nothing but it consists of closely spaced absorption lines. Means your atomic absorption lines can be far apart from each other, but molecular absorption spectrum are so close to each other that they can be designated as a band spectrum. Now, what is EMR? Emission of radiation. EMR is produced when an excited particle, ions or atoms or molecules, relaxes or gets back to its lower energy levels by giving up their excess energy as photons. The common phenomenon which we all know are the fluorescence and the phosphorescence. You can see in the first part of the figure, absorption, a photon has excited to higher energy level by absorbing energy, and in the second part from E2 to E1 it has released energy h mu, the same amount, and it is coming back to its lower energy state, that is E1. Now, if we try to understand again emission in different categories, then we can say that atomic emission happens because of atomic particles which take parts in the gaseous states and they emit radiation containing only few wavelengths. Discontinuous spectrum or line spectrum can be obtained. Then another important thing is atomic particles, closely packed particles or molecules produce continuous radiation which can give in turn continuous spectrum. So we can say that atomic emission can happen in the form of discontinuous spectrum as well as in the form of continuous spectrum. Okay. Now the third category are the solid particles. These are heated, means thermal radiations are incident to it, and they produce again continuous spectrum. Now, electromagnetic spectrum and the atomic and molecular processes associated with it. Molecules undergo processes like rotation, vibration, electronic transitions, and nuclear transitions. These energies underlying these processes correspond to different regions in the electromagnetic spectrum. So let's say, to start with, radio frequency waves. These are low energies that correspond to energy difference in nuclear and electronic spin states. So radio frequency waves actually deal with nuclear and electronic spin states. These are the things which respond to the sample when you incident a radio frequency to the sample. Now, applications in nuclear magnetic resonance and electron paramagnetic resonance spectroscopy. Radio frequency and nuclear magnetic resonance are widely used in imaging, especially in medical field. They are used in MRI, magnetic resonance imaging, which is a very important technique, very crucial medical technique, which is used for diagnostic purposes. Now, the second category are the microwaves. What are microwaves? These are energies between those of radio frequency waves and infrared waves. Applications in rotational spectroscopy and electronic paramagnetic resonance spectroscopy. The third category is infrared radiation. What is it? Molecular vibrations fall in the infrared region of the electromagnetic spectrum. So molecular vibrations are related to infrared, whereas radio frequency waves are related to microwaves, and we can say that nuclear and electronic spin states are related to radio frequency. So infrared spectroscopy is therefore also known as vibrational spectroscopy because it perturbs molecular vibrations, and it is very useful technique for functional group identification. Like you have put, let's say, an organic compound into the sample and you are radiating it with infrared frequencies. So the spectra which you will obtain, if you analyze it properly, then you can have idea of functional groups attached in the organic compounds or the compounds present in your sample. So this becomes the application of infrared radiations, or the application of the technique involved with the infrared radiation, that is infrared spectroscopy. Now, the fourth and very important and the most common type of technique, which uses UV visible radiation, gives UV visible spectroscopy. It is involved with the electronic transitions. You must have heard about HOMO, LUMO, and all the electronic states like sigma, sigma star, pi to pi star. All these transitions are nothing but electronic transitions taking place in chromophores. Chromophores are very important part of UV visible spectroscopy. UV visible spectroscopy is most sensitive to colored compounds, especially colored compounds means those who have chromophoric molecules into them. Now, UV visible region involved in electronic transitions in the molecules, use of UV or visible light therefore comes under the electronic spectroscopy. The next category is X-ray radiation. These are very high energy electromagnetic radiations. Transitions happen in the internal electrons of the molecules. Now, just to give a short picture, what are the common types of useful spectroscopic techniques? The first one and a very important one is fluorescence spectroscopy. We will study about this in our next lecture series in detail. The fluorescence spectroscopy, the phenomenon, it's used in medical fields and applications. But here, just we need to understand its kind of emission phenomenon, and fluorophore is required to emit the fluorescence. The second category is X-ray spectroscopy and crystallography. Flame spectroscopy, which has three categories: atomic emission, atomic absorption, and atomic fluorescence. And we can categorize it as AES, AAS, and AFS. Okay. So the next one is plasma emission spectroscopy, spark emission spectroscopy, UV visible, as I told you, IR spectroscopy, Raman, NMR spectroscopy, nuclear magnetic resonance spectroscopy, photothermal spectroscopy, thermal infrared spectroscopy, and mass spectroscopy. Now here, mass spectroscopy is a very important technique. It's not exactly a spectroscopy, but it's sometimes known as mass spectrometry because we measure actually the amount of disintegrated fragments of a compounds. We actually measure M by Z ratio, mass upon atomic number ratio. Now, what are the basic principles of molecular vibrations? So, absorption in the infrared region is due to the changes in the vibration and rotational levels that we have already considered in our lecture now. With low energy radiations, molecular rotations occur. With high energy radiations, molecular vibrations occurs. Now, this we need to actually understand that low energy radiations always produce molecular rotations, while high energy radiations always will lead to molecular vibrations. Now, this is the difference between molecular rotation and molecular vibration. Now, due to IR radiation energy, a vibrational rotational spectrum is obtained. The vibrational energy depends upon the following points: masses of atoms, strength of the bonds and bond distances, the arrangement of the atoms in a molecule. Okay. Now, the table of relation. We will discuss here the table of relation between spectroscopy, type of radiation used, wavelength, related energy, what it exactly does to atom or to molecule, what it tells about us, the atom, about the atom or the molecule. So to start with, photo-electron spectroscopy, it deals with X-rays, wavelength 0.01 to 10 nanometer, energy very high, removes 4 electron, and what information we can get, atomic structure we can get, and how tightly the electrons are held by the nucleus, and identity of an element can also be understood. UV visible spectroscopy, again, it is related to ultraviolet region of the electromagnetic spectrum. Wavelength 50 to 400 nanometer. 50 to 400 means UV also is involved, not only visible. Okay, so relative energy it's high, excites valence electrons. Identity of a molecule or element can be known. UV visible spectroscopy, again, when it deals with visible light, then 400 to 800 nanometer, then relative energy can be medium, excites valence electrons only, and concentration of a molecule can be known. So, if a molecule is highly concentrated, then probably its UV visible spectroscopy will give absorption, a very high value of absorption at a particular wavelength, while the less diluted, the less colored, the faded ones will give you low absorptions at a particular wavelength. Okay, now vibration spectroscopy uses infrared radiations, and types of bonds or atoms or functional groups can be known. Whereas microwave or rotational spectroscopy, it deals with the location of hydrogen or atoms within a molecule. So a particular region of EM spectrum, how it is related to spectroscopic techniques. So gamma rays is related to Mossbauer spectroscopy, X-ray with X-ray diffraction and X-ray fluorescence. UV and visible is related to UV visible spectroscopy, atomic absorption spectroscopy, fluorescence spectroscopy, phosphorescence spectroscopy. Infrared is related to infrared spectroscopy and also Raman spectroscopy. Microwave is related to microwave spectroscopy. So easy to remember and easy to understand. The names are related to the techniques involved. Now, we can see here a conical flask, atom in the sample. Now, atomic emission spectroscopy helps us to exactly identify what atoms are present in the sample. Hence, the name given is atomic absorption spectrum. So, as I told you earlier, three categories are there: atomic absorption, atomic emission, and atomic fluorescence. What is the difference between AES and AAS? AES examines the wavelength of photons emitted by atoms or molecules during their transition from excited state to a lower energy state, whereas AAS measures the loss of electromagnetic energy after it illuminates the sample under strain. Point number 2, each element emits a characteristic set of discrete wavelengths, whereas energy in certain amount is absorbed during transition to the higher energy level. The third point, by observing these wavelengths, the elemental composition of the sample can be determined, whereas in AAS, amount of energy absorbed gives estimate of the concentration of the analyte in the sample. Now, types of molecular spectroscopy, again a table I'm presenting here to help you to understand how easily a technique can be, spectroscopic technique can be related to the radiation type. And all these radiation types are actually the types of molecular spectroscopy. Now, the very important phenomenon that leads to the spectroscopic techniques are the selection rules. So there are certain rules that molecules and atom needs to follow to allow or forbid a certain kind of transitions. So not all transitions are actually possible. For an electron to transit or to emit, certain quantum mechanical constraints apply, and these are known as selection rules. For example, an electron cannot change its spin quantum number during a transition. These are forbidden. These are not allowed. Okay. Simply, the other examples include number of electrons that can be excited in one time, symmetry properties of molecule or symmetry of electronic states. We already have studied in the module atomic structure in first semester what are the different states of or different kinds of quantum numbers and what are the rules that they need to follow, what all principles that need to be followed for a transition to happen, especially electronic transitions already we have studied. Okay, so here we will just consider the selection rules which are actually important for a transition to allow or to forbid. So to further complicate matters, forbidden transitions are sometimes observed as low intensity due to lot more factors. In this slide again, if I repeat, only a fraction of all possible transitions are observed. So allowed transitions are high probability transitions, high intensity transitions, electric dipole moment interaction transitions. Whereas forbidden transitions are happening because there is very low probability, intensity is very weak, then electric dipole interaction is actually not there. Now, selection rules for allowed transitions, the polarity of upper and lower level must be different. So the parity of the upper and lower level must be different and the parity is odd, okay? So if delta J is nothing but angular momentum. So first we will try to understand what are the quantum numbers for individual electrons. We have already studied these things, but let's just take a quick revision of this. So N is nothing but principal quantum number. L is azimuthal orbital angular momentum quantum number. ML is orbital magnetic quantum number, whereas MS at the last is nothing but spin magnetic quantum number. S is electron spin quantum number. Allowed values and symbols I'm not going to dictate in or explain in detail because we already know these. So now how we will use these symbols of quantum numbers to understand the atomic selection rule. So what does atomic selection rule states? It states a principle given by Russell Saunders, which is known as Russell Saunders, which is known as Russell Saunders coupling. So according to this coupling, delta L should be equal to plus minus 1 for one electron change only. Delta capital L should be 0 or plus minus 1 resultant orbital angular momentum. Delta S, which is resultant spin angular momentum, should be 0. Total angular momentum, that is delta J, can be 0 or plus minus 1 only. Now, if we take example of diatomic molecules, we can take the symbols first. So L is total orbital angular momentum, capital S, total spin angular momentum, projection of L on the internuclear axis, and then projection of S on the internuclear axis, and then there is omega, which is sum of projection of L on the internuclear axis and sum of projection of S on the internuclear axis. We will try to understand this in the form of molecular selection rule. So molecular selection rule means when we are not talking about atoms, we are talking about more than one atom. It means we are talking about molecules. So electronic configurations of multi-electron atoms or molecules can be explained also by LS coupling, Russell Saunders coupling. So it states that the total angular momentum ml can be summation of ml, whereas L can range from minus L to 0 to plus L. Similarly, ms also equals to summation of spin magnetic moment, and S can range from S, then S minus 1 to 0 to minus S. So here is a small denotation which can help you to determine the molecular selection rule. ML or MS defines the microstates and L and S defines the states, that is collection of microstates. So this we need to understand. Groups of microstates with the same energy are called terms. So what is terms and what is micro steps can be understood from here. Now, these are different types of molecular energies as I wanted to show you in our previous discussion. We can see here that there are electronic states which can excite to higher energy level and then come back. There are rotational states which can, again, they have their own energy states, and then there are a lot of vibrational states also available. Now, to indicate molecular rotations, we can understand what kind of rotation transitions is possible, especially when a sample comes in contact with a microwave, or what kind of vibrational transitions are possible, especially when a sample comes in contact with infrared. So potential curve representing the ground electronic state, how this curve indicates the different rotational levels and different vibrational levels, and how an electron can be allowed from a lower rotational energy level to a higher rotational energy level, whereas how an electron can also jump from a lower vibrational energy level to higher one. Now, rotational spectroscopy also has a particular selection rule. So if we try to understand selection rule of a rotational spectroscopy according to Bohr's postulate, it gives us three conditions. Delta J can be plus minus 1, delta J can be plus 1, which will lead to absorption, and delta J can be minus 1, which will lead to emission. Vibrational energy. Now, we have an, we came across a lot of time different terms like bending, stretching, or wag, that is rocking of a bond. So what are these? These are the vibrational forces involved in a particular molecules. We know that vibrations are related to energy, and energy is related to nothing but frequency. The appropriate frequency for a molecular vibrations are in infrared region of the electromagnetic spectrum. Vibrations, therefore, is forming a fundamental basis of spectroscopy. Now, we can say that vibration of bond is occurring in all the three states of matter, liquid, solid, and gases. So, how does vibration helps us with the spectroscopic techniques, and what information we can get? We can get functional group determination, we can get structural identity, especially fingerprinting comes under the vibrational energy spectroscopy. Now, what is transition probability? Transition probability is probability of a particular transition to take place in a single step. So let's consider two wave functions, psi1 and psi2. So transition probability of one molecule from one state, that is psi1, to jump to another state is psi2 is known as probability transition. Okay, so for an electron transition to be allowed, the transition moment integral must be non-zero. This is the rule for transition probability. Again, the very next and related term is the transition moment, or it is also known as transition dipole moment. Transition moment is the transition between initial state and final state, and is the electric dipole moment associated with the transition between these two states. So, for example, when a beam of light impinges on a sample, then part of light may be absorbed, the precise amount depending upon the wavelength. So, the quantity that determines the probability of a transition to take place in the transition dipole moment is actually the dipole moment value. Okay, whereas the probability was simply known as the chance, that is transition probability. So here with this figure, you can try to understand how transition probability is related to transition moment. Now this is a table at last which I just want to show you that how type of electromagnetic wave is related to the production of different phenomenon, and then how it is related to the applications of different techniques or applications in our daily life, and how life sciences and other kinds of technological fields are being impacted, and also what drawbacks we are facing with this particular kind of technique. Thank you.